Hi everyone! In this video I want to take you through how you can easily introduce parallelization into your bioinformatics code using the joblib library in Python. One example of where you can do this is for the common task of counting kmers in a fasta file. And just in case you are new to one or more of these concepts, I will briefly explain. So what is a kmer? A kmer is simply the term we use to describe a tiny piece of subsequence of DNA. A 5-mer would be a sequence of 5 nucleotides. A 6-mer would be a subsequence of 6 nucleotides. And an 11-mer would be a subsequence of 11 nucleotides, and so on. That's really all it is. So now, what is parallelization? If you're not familiar with coding in parallel and you haven't done much machine learning using GPUs, it's likely that the vast majority of all the code you have written would have been executed sequentially, as sketched here on the left side. Imagine you have your CPUs and you have 8 cores and you have your calculations 1 to 10 coming in to be executed, and then it's just one core doing all the workload. You might feel your code is already snappy, but when you get into analysis of big data files such as DNA, then executing sequentially is not efficient anymore. You can therefore imagine using multiple cores will speed up your execution time drastically. As you can see here on the right hand side, you can utilize, for instance, 4 of them. In this case, core 1 is taking the calculation 1, 5 and 9, 2 is taking 2, 6 and 10, and so on. That being said, not every task is actually easily parallelizable, but those that are, we often refer to as embarrassingly parallel. Luckily, iterating through a fasta file with multiple entries and then counting the kmers is such an example. But what is a fasta file? A fasta file is simply a text file for representing DNA or protein sequences, and the generic file extensions include .fasta, .fas, .fa, .seq, and .fsa. And every entry inside the fasta file starts with a header as indicated by the greater than symbol and a label that helps you to identify the particular sequence. So here is one entry, and here is another entry from the same fasta file. And then what follows for each entry are the nucleotides or the amino acids that make up the sequence. Because we have multiple entries, we can therefore easily redirect Python to take each entry and give them to an individual core, and hereby help us speeding up the tasks. And we can even have the results collected again in the correct order, as this is otherwise not an obvious task for the computer to do. So let's get started. For this tutorial, I will be iterating through the human genome, and I will count the occurrence of all kmers with a length of 5. The human genome has sufficient entries to allow us to see the benefit of applying parallelization. But of course, this concept applies to any fasta file or any genome out there. It doesn't have to be the human genome. So look into the description for a link to the same fasta file if you want to follow along. First, we will be importing all libraries, and we will only be needing a tiny handful. We will be importing OS, sys, and time, and then from joblib, because we're not going to import everything. From joblib, import parallel and delayed. Actually, one module here. I'm going to say from collections, import counter. And you'll see why later, of course. Remember that I told you a fasta file is typically made up of multiple entries, and each entry is indicated by the greater than symbol. If we make a list that tells when an entry start and end, we can easily and fast assign new tasks to any available cores. So this would be position 0, and this might be position 300, or whatever in a document. Then we would have position 301, and then we would have position 600, or something like that. Generating these indices are usually not the bottleneck with regards to speed, so feel free to do this computation in any way you want. I will show you one of the fastest ways I'm familiar with, but don't freak out, as this has nothing to do with the parallelization itself. The parallelization step is way more simple. The first thing we want to do is write a function that can open a fasta file and then index it like I just showed you. So we'll define fasta indexing that takes as input the file name to the fasta. Then we want to open the file as a binary, because reading in binary is usually always faster. And we will assign that open file to the variable in file. So the next thing I have done is to actually define a chunk size of 1024. First, I told Python to open my fasta as a binary, and next up I set a chunk size, which means that every time I will be reading a piece of the file, it's going to take this chunk. And reading in chunks is actually one of the fastest ways after you have assigned, the binary reading up here. And this is a really important thing to know when reading files in high performance computing. So now I have started defining a loop to read the whole content of the fasta file. And when the length is 0, it's going to stop. Next up, we will start by looking for the headers, which are indicated by the greater than symbol. So we'll say content and use the find function and look for the binary representation of the greater than sign. And then we will append to the head start list. And the same way that we found out where the header starts, we will also define where the header ends. So once again, we look in the content and we find where the binary of \n exists, and then we can append that to our head end list. And then it's very important to remember to close the file, because if you loop over a genome file that takes up many gigabytes and you open it for every time you have an entry in your fasta, you could end up massively overloading your RAM. So remember to close the file after this loop. Next up, I have inserted a piece that will look for wrong headers. Basically meaning we have an extra greater than symbol in our header line. And we simply we'll go ahead and then delete this index then. And now eventually, after we have gotten to know where the header ends and start, then if we add the value of 1, that will be 1 position after the header ends, we will actually go into the place where the sequence is starting, like I showed you in the Word document. And the same goes for where the sequence starts. If we subtract the value of 1, we are now back to where a sequence ends. So now go ahead and append these values to a list called fasta index. You will append the position of the sequence start, and you will append the position of the sequence end. And then lastly, by subtracting the sequence start from the sequence end, you will in effect get how large this sequence is. And that will be useful in just a moment. So what I have done now is add a simple line that's gonna look at all these sizes, and then it's gonna sort them. And the reason why we want to sort them is to have all the cores work equally as much. You can imagine one core has a really large job in the end after all the other cores have done running. Then nothing can progress until that last core is done. So it's really important to balance all this work. And finally, we will return the fasta index. So this concludes the first function. We are reading a file in binary. We are reading it in chunks with a chunk size we defined. And we are reading it until there's nothing more to read. What we are doing is to look for the headers as indicated by the greater than symbol. And then we find out where they end. And then we eliminate wrong headers. And then we assign where the sequence start and end. And we append those to a list called fasta index. And this is the load balancing function that's looking into the third number in the tuple. So now I think it makes sense to try and run this function so you can see what the output looks like. And we will be writing the main part of a code with the main block here. And the reason why we want to run our code like this actually have to do with initiating child processes later on. I happen to have a small test file from the human genome, and it's a very tiny test file, as you'll see in a moment, but it's just to show you what kind of output we are expecting to get. So next up, go ahead and define your Kmer length. So let's set a length of 5. Next up, I have generated something called a translation table, and what it's going to do is look for all kinds of unwanted characters that we don't want for our analysis and when sort of browsing through the DNA, and it's going to convert them all to the same character, which is capital N in this case. And the capital A, T, C, and G we do want to keep. I just convert them to lowercase. Next up, I have assigned a variable called nworker. So the OS module actually has a function called CPU count, which will go into your system, and it's going to read the number of logical cores at your disposal. So it's the maximum number of logical cores on your system. We won't necessarily be needing it, but it's good to know, and we will get into that in just a moment. So let's now go ahead and try and finally return the indexes for the test file. So keep in mind, this is not the parallel part yet. It's gonna happen later. And notice also I'm timing everything. It's a really good habit, which will help you identify bottlenecks in your code later on regarding which pieces of code takes up a lot of processing or a lot of time to process. Yeah, so let's end by printing how long it took, and let's try to run it. And I see we get an error. Yeah, we need to just add an additional bracket here, of course, because we are making tuples. that we append to the fasta list. And also I noticed something critical as well. We should move this to the left, because after there is no more content, after this loop is done, is when we want to close the file, of course, and not before. So we look for where the header ends, and then we close. Let's try to run the code one more time. And I think this is about right. If I open the myIndex variable, we do have a list containing tuples. And they should be sorted by the largest fasta entry, the smallest, my bad, to the largest entry. And here the file claims we have 30, because we have 0 indexing, so 30 entries. And I happen to have the test file lying around. So this is what a fasta file looks like. And we have the header, of course. This is sequence 1, the first sequence. And let me scroll all the way to the bottom, because I know I can find the last entry just around here. And there we go, 30th sequence. Let's go back to this list. And we do indeed have 30 entries. And they are sorted from the smallest to the largest, meaning not the same order, but in order of size. Okay, so now we are essentially ready to start finding our kmers, and I will start writing a new function for that purpose. It's going to take our fasta file, the human test in this case, and it will take the indices we just were able to acquire, the one called myIndex in this case. So once again, we will open the fasta file by using open function, and we will be reading as binary. Next up, Python has a really genius function called seek, which will essentially just set a pointer the same way I'm setting my pointer now, anywhere in the document. And this is the position where it's going to put it. And that position is the index we just acquired from the function above. And then it's going to use read. And what it's going to read is basically all the content in between these two indices. And it's going to assign it to the variable called sequence. But before we do that, we also use the translation table, which will get rid of all unwanted characters that might be in our fasta file. It's also going to take care of stuff like skipping lines here. And lastly, you need to remember to close the in file. And once again, the reason is that your DNA file might take up a lot of space, and it's going to open it 30 times because we do have 30 entries. So it's going to eat a lot of memory really fast. So remember to simply put .close. Next up, we will be assigning a subdictionary to keep track of all the kmers that we will find with each parallel process. And next up, there's actually another trick up our sleeves that we can take advantage of to save time, because usually large DNA files will contain a lot of undefined nucleotides, which are these ends here. I hope you can see this, but basically we have our sequence starting and then a lot of undefined nucleotides. But it's not just 2 lines. It can be hundreds of lines in a real DNA file. And there's no reason for the computer really to look for kmers in that area, because it's not going to be useful anyway. So let's define a function that can skip all those regions and jump only to where the DNA starts. And we will be calling that function index sequence. I know that was just a bit of a mouthful, but let me briefly take you through it. This function takes the sequence as the input, and that sequence is the one we opened down here. Then we create an empty list. Then next up, we will be looking for the first time in the sequence that we are hitting a lowercase a, t, c, or g. And this comma needs to be gone. There we go. After we found out the a, t, c, or g, we will take the closest one of those with the min function, meaning it could be either a, t, c, or g, but the start of the sequence will be whichever of these appears the first. And then we will basically go on until we hit the capital N, and we will have the capital N due to the fact that we apply a translation table down here for all unwanted nucleotides. They are all transformed into capital N. After we know when the capital N appears, we can set that as our sequence end. And that's basically all this function does. And then we append the real start and the real end, and we return this whole list. So let's move back to our find kmers function, where we have now defined the sub-indexing variable. So all that is left now is basically just to loop through the sequence and find our kmers, and then add them to the dictionary we have up here. So I will say for start, stop in sequence index, which means we will take the real start and the real end. And then we will say for I in range start to stop minus kmer length plus 1. And kmer length is the one we defined down here, which is 5 in this case. So we are looking for 5 mers. And then we will say that kmer is equal to sequence of I colon I plus kmer length. There we go. And now it's time to add this kmer to the dictionary, or count it if it already exists in the dictionary. So we will say if kmer not in subdict, then subdict of kmer will be equal to 1, else subdict of kmer will need to add the value of 1. And this function has to find kmers, but it's going to return then the dictionary for a single entry, right? So we will return the sub-dictionary. So let's take a step back and let me remind you that we have 30 entries in this particular FASTA file. It's just a test file, but the concept is the same when we scale up to the full genome. We have 30 entries for this particular test file, which means that this function will in effect have to run 30 times, meaning we get 30 different sub-dictionaries. And these will have to be merged later in order for easier counting and analysis, of course. But now that the function is done, all we have to do is basically implement the parallelization step, which is way more easier than you would actually expect. Let me just write a quick text here. Indexing time, just to keep track of what time are going to be returned. The result of the parallel process will be assigned to the variable results. And all you have to do to actually make it parallel is to type parallel, number of jobs, how many cores do you want to distribute it to, and remember that we assigned n worker, so we can put that here, meaning that the joblib library will try and utilize the total amount of logical cores on your system. So this is just how we're going to start, and I'll elaborate on later why it's not necessarily the best thing to just utilize the maximum number of cores on your system. But for now, let's just go with it. So after having assigned the number of logical cores, you will have to use the delayed function. And the function you want to parallelize, you put in here, which is our find kmers. So you type that inside here, and we will use the file as our input. So next up you have to put the input for that particular function. That will be file, and it will be all the different indices that we found originally, which were assigned to my index here, sorry. So it takes the fasta input, and then you could refer to all the indices as C for C in my index. And that's really all you have to do to implement parallelization for your code. And the same way that we timed our indexing, we can also time how long it takes to count all the kmers. Actually, I don't have to print. I will just actually copy this line here. And instead of index time, we can call it, I don't know, something like count time. And we will print how long it takes to count them afterwards. Oops, that's my bad. We need to end it with apostrophe, and then we'll print the count time. So now let's see if this works. I'll hit run. Okay, and it looks like we are getting an error in the translate. That's because there is not supposed to be a dot here. Let's try and run it one more time. And it seems like I did not manage to spell parallel properly. Let's try again. Argument should be integer or byte-like object, not string. Oh yeah. When you point to the A, T, C, or G's, that also needs to be binary. So drop a B in front of the string here, because we did read it in as a binary. So of course we need to stick with that. Let's try and then run it one more time. And I feel like we succeeded. As you can see, we now have successfully managed to make a list, and the list contains 30 dictionaries, a dictionary for every entry in the fasta file. So let's try and open one of the elements in the list. And as you can see, we have the counts for all the individual title strings. And you can even sort them by the number of counts it managed to get. The reason the size is 1024 is because that is the maximum number of combinations you can make with these 4 letters, given a string with a length of 5 or 5 mers. And of course, imagine the fasta file is shorter. You might not experience all these combinations, but even this test file is quite diverse, and the DNA seems quite shuffled. So I'm not really that surprised that we experience all the combination of 5 nucleotides. But let me solidify this point. So if we change the kmer length to 6, Let's open the results one more time. And now you can see we don't actually reach the full number of combinations for every entry. As you can see here, we're able to get 4,096 as the highest number. And that's because that's the number of possible combinations you'll get for 4 letters with a sequence length of 6. But for the first couple of entries, we do not actually explore all that diversity. It simply doesn't exist. So the dictionary will never expand to a size larger than what it sees, of course. So now that you sort of know how this all works, you can imagine it's quite painful to have to use a calculator or an Excel to put all these numbers together, because of course the string AAA will appear many times, and we want to put these numbers together. So let's write a brief loop for that. We still like to have everything in dictionaries, so let's call this variable final dict. And yeah, let's just time it one more time, because timing is nice. And we can say something like for R in results, for mer key in R keys, if mer key in final dict, then to final dict simply count, or if the mer key is not there, then go ahead and add it by saying R equals to R for mer key. And that's basically it. And to finish off, let's stop the timer, so we can say merge dict time is equal to time.time minus start. And then for the sake of saving random access memory or RAM on your computer, go ahead and delete some of these variables. It's just a good habit to do. And if you do get into really large DNA files, like FASTA files, you should really consider if you want to delete variables to save yourself some pains. Let me just check if that's all. Yeah, of course, we have all these times printed. So let's also print the last one. Let's just print it as merge time. But let's also print the total time for this whole process. That's really easily done by taking all the variables and simply adding them together. So we have merge dict time, count time, and what was the other one? Index time. So let's try one more time to run the program with 6 kmers. Float object. Okay, so all right. So after some time, I just realized I mistyped up here. It was a typo. Let's try and run it again. If we are rounding and we do want decimals, we need to set a comma, and then we can put 3 here as well. And yeah, as you can see, we get something that's much more sensible now. I actually ran it a few times because I thought I had a bug, but I did not. And we get a total time of almost 7 seconds. The index time is pretty fast. The count time is really what takes up most of the computational time. And then the merging is definitely slower than indexing, but no way as slow as counting. But in order to really get a sense of how parallelization can actually benefit us, we need like a bigger file. This human test file is simply not big enough. It is 1.6 megabytes, but the human genome, my version at least, is 3.1 gigabytes, so quite a difference. So let me change the Kmer length back to 5, and I happen to have also the human genome on my computer. and it's just called human.fsa. So now we are basically ready to run the full human genome. I will get started. It's running now. And as you can see, the indexing time took quite a bit longer, but still not long compared to the final time, which I will show you later. And before cutting the video off for a break while it's running, I will briefly show you the systems monitor. As you can see, everything is running at 100%, meaning we are utilizing all the logical cores. So I'll see you back soon when it's finished counting the kmers for the human genome.
Much later.
So now the counting has finished. As you can see, it took a total of 427 seconds. The indexing time, like I mentioned, was pretty fast. The counting was the part that took the longest, and merging was really fast. And this was utilizing all 8 cores. So what happens if we go to 1 core? I started running with 1 core now, but I'll see you back again after we have finished running with 1 core. So not in parallel, but completely sequential.
6 months later.
So now we're back again, and as you can see, the task took more than 1000 seconds to complete. Again, the indexing time was fast. The counting took up the vast majority of computational time here. But why is using 8 cores not 8 times as fast? And the answer is not really that simple, but I'll try my best to give you an explanation. So I actually took the effort to count 5, 7, and 9 mirrors for the full human genome using 1, 2, 3, 4, 5, up to 8 cores. So if we start by looking at counting 5 mirrors using a single core, we achieved it in less than 800 seconds. Increasing to 2 cores actually did not twofold the efficiency, and the same goes for 3 and 4 and 5 cores. And moving beyond 5 cores actually starts to become a disadvantage. And it all has to do with the size of the job combined with the time it takes to initialize a new process, and then scheduling. So if the job is sufficiently small, it's not a benefit for you because it takes time to initialize new processes. However, as we move to 7 mirrors and 9 mirrors, it becomes much more beneficial because there's much more information to keep track of, meaning the job will take much longer to complete. And you can imagine moving beyond 9 mirrors, it's going to be even more a drastic change when you go from 6 to 7 and 8. So the short answer is, it depends on the size of your job. The larger the job, the more beneficial it is to distribute among cores. And of course the same goes if you are using a high performance computing cluster with many nodes. It takes time to split the information and gather it again. So that is basically it for this video. I hope you learned at least a little bit and are able to integrate some parallelization into your bioinformatics workflow. If not, maybe you would be able to apply it to some other code you're doing. Nonetheless, learning how to program basic parallel or embarrassingly parallel problems can really be powerful. So definitely make it a consideration. And I will briefly acknowledge Peter Vel from the Technical University of Denmark, who provided a lot of the code shown in this video. And he also runs a great course on high-performance computing in life science. And I hope to share more content related to this topic in future videos. So stay tuned by subscribing to the channel, and I hope to see you guys in the next one.